it can be really hard to look at a set of vectors and have an intuitive sense of whether or not they're linearly independent. So there's a mathematical way to determine whether the set of vectors is linearly independent or linearly dependent, and this is where the mathematical equation helps us formulate that. We know what to visualize geometrically. The set of vectors is linearly independent if it's not possible to place the vectors together tip to tail and arrive back at the origin. If it is possible to arrive back at the origin by using at least one non-zero constant on those vectors, then the set is considered linearly dependent. So the general definition, mathematically, what that pans out to is if you can apply scalars to these vectors x1 through xn, say we have n of those vectors, and it's possible to generate the zero vector, we say that if the only way you could do that is for all of those coefficients to be zero, then the set of vectors is linearly independent, meaning we can't place them together tip to tail and arrive back at the origin without reusing the same vector. If, on the other hand, it is possible to find constants that are not all zero, then the set of vectors is said to be linearly dependent. So what this amounts to is solving this system of equations, and we can determine linear independence without having to use our intuition, especially where it's not possible to do so. So this set we've already looked at in one of our earlier videos in this lesson. Consider these three vectors. This collection of vectors is linearly independent. As we can see, you can take, for example, 3 times 1, 0, plus 2 times 0, 1, minus 1 times 3, 2, and that will give you the zero vector, and those coefficients are not all zero. In fact, none of them are zero in that case. But let's do this according to the mathematical definition. Let's say that these were more complex and we couldn't just eyeball that. We couldn't just sketch it out and draw a meaningful representation. So what we're trying to do is we're trying to find, is there a C1 times x1 and a C2 times x2 and a C3 times x3 such that I get the zero vector? Well, this is something that we can solve for. We can solve for these three variables by using Gaussian elimination. And our matrix, our augmented matrix for this system of equations would be 1 for C1, 0 for C2, 3 for C3, and then 0 for our constant. And then in the second row, 0 C1 plus 1 C2 plus 2 C3 equals 0. And this is the system that we're trying to solve. So if we produce the reduced row echelon form of this using some form of technology, well, surprisingly, what we would get is 1, 0, 3, 0, and 0, 1, 2, 0. This system is already in reduced row echelon form. And let's recall here that this column is the coefficients of C1, coefficients of C2, C3, and our constants. And so let's make mathematical sense of this. This says that in our first row, our first leading one occurs in the C1 column, so C1 is not free. In our second row, our first leading one is in the C2 column, so C2 is not free, and we've run out of rows. There's no leading one in the C3 column for any of the rows, therefore C3 is free. So that means that let C3 equal some constant. Let's call it S. Let's not use C again to avoid some confusion. So C is just some real number. So let C3 equals S. And just to remind ourselves, what we're doing here is we're saying pick a value for C3 without giving it a numerical assignment, and let's call that value S. Well, therefore, this says that C1 plus 3C3 equals 0. And since C3 equals S, we could solve for C1 here and write C1 equals negative 3S. In the second row, C2 plus 2C3 equals 0. which translates to C2 equals negative 2C3. But C3 is set to S. So what solution set do we get for C1, C2, and C3? Well, that vector equals C3 is S, C2 is negative 2S, C1 is negative 3S. Now, this is a homogeneous system, so notice that we do not get a vector of constants. If we broke this up into a vector constant vector, and a parameter vector for S, we would get 0, 0, 0 minus or plus negative 3S, negative 2S, and S. So let me factor that out to write it in parameterized form. And so what this indicates is that there are infinitely many solutions for C1, C2, and C3. Infinitely many choices for C1, C2, and C3. How do we generate those choices? Well, we have to specify a value of S. So for example, if S is equal to 1, then we could have our vector, our solution, be negative 3, negative 2, and positive 1. So if you take negative 3 times the 1, 0 vector, plus negative 2 times the 0, 1 vector, you get negative 3, negative 2, plus 1 times 3, 2. Well, those components will cancel out, the negative 3 plus 3, negative 2 plus 2. If you let S equal negative 1, then you get positive 3, positive 2, positive 1, which were the coefficients we mentioned at the beginning of this video, as well as the coefficients we implemented in our earlier example. Now, we could keep on going. There's infinitely many different values of S that would make this equation true. And so, since there exist C1, C2, C3, not all 0, the set is linearly dependent. The set of vectors x1, x2, x3 is linearly dependent. Okay. This was an intuitive example. We'll take a look at one more here where we have, say, the vectors 1, 0, and 0, 1. Again, another example that we looked at. And if we call this x1 and we call this x2, what we're searching for is, are there constants c1 times x1 plus c2 times x2 such that we get the 0 vector. And this is not going to be a very interesting reduced row echelon form, but we could set up our system, coefficients of c1 and c2, and our constants in this system. So we'd have 1, 0, 0, 0, 1, 0. Now this is already in reduced row echelon form because it satisfies the definition that in each row we have a leading 1. Above and below a leading 1 there are zeros. And all the leading 1s appear to the right of leading 1s in the rows above it, and there are no rows of zeros, so we're in this reduced row echelon form. So what does this imply? Well, since this is already reduced row echelon form, this means that C1 is equal to 0, and 0 C1 plus 1 C2 is 0, so C2 equals 0. So the only way for this equation to be true, in other words, the only way to get back to the origin, is to never leave it in the first place. So since C1 equals C2 equals 0 is the only solution, and both coefficients are 0, this set is linearly independent. As we've illustrated before, this 1, 0 vector can only take you left or right. The 0, 1 vector can only take you up or down, and therefore you can't take the 1, 0 vector away from the origin and then arrive back by only taking a multiple of the vector that takes you up or down. Now, here's where this definition becomes more handy. Let's say that we have these 3 vectors, and you look at them and you think, well, it's not very obvious as to what this looks like geometrically, because we're in 3 dimensions here. And not only is that not obvious, but it's kind of hard to draw them and try to develop any sense of intuition. So I could check whether these are linearly independent or linearly dependent by again applying the same definition. What constant C1 times 9, 36, negative 12, plus what constant multiple of 3, 2, 1, plus what constant multiple of 0, 6, negative 3 will allow me to get to the origin. If the only values are C1, C2, C3 are all 0, then this set would be linearly independent. And you might look at it and you might think, well, it looks linearly independent, but that's not good enough. Just because we can't see it doesn't mean it's not there. So if I set up a matrix for this, my coefficients of C1, C2, C3, and my constants, I'll have 9, 3, 0, 0, 36, 2, 6, 0, negative 12, 1, negative 3, 0. And now I need to row reduce this. So I'll do that off to the side and we'll write down what the reduced row echelon form is. So here I have it, and we look at this and we see that for our variables, well, first of all, we do have a solution. There's not a row in which there's, say, 0 equals 5, so nothing funky going on. And in the first row, our leading one is in the C1 column. Row 2, our leading one is in the C2 column. Row 3 doesn't have a leading one, so that means C3 did not have a leading one in its column, so it is free. Now at this point you could really stop, because if there's a free variable, that means that there are going to be infinitely many solutions, and that means there are infinitely many choices for C1, C2, and C3, which makes the set linearly dependent. Okay, so this is going to be linearly dependent if we end up with a free variable. But let's just go ahead and establish that more clearly. So let C3 be some constant. The first equation says that 1C1 plus 0C2 plus 1/5 C3 equals 0. And that translates to C1 equals negative 1/5 of whatever C3 is, which is S. Second equation says 0C1 plus C2 minus 3/5 C3 equals 0. So that means that C2 is going to equal 3/5 of S. So our solution would be C1, C2, C3 vector equals, we'd have negative 1/5 S, C2 is 3/5 S, and C3 is 1S, and I'm just going to go ahead and factor that S out right away. So once again, we see that there are infinitely many choices. You could let S equal 1, for example. You could let S equal 2 or negative 1, or if you let it equal 0, yes, it will make C1, C2, C3 all 0, but that's not the only solution. As an example, and the way I constructed this is that really this first vector here, which seems to have unusually high values, is actually twice the second vector plus 5 times the third vector. Let me show that to you. If S is equal to negative 5, then I multiply the components by negative 5. Negative 1/5 times 5 is 1. 3/5 times negative 5 is actually, let me choose positive 5 here. So that would make this negative 1. Then I'd have positive 3, and here I would have 5 times 1, which is 5. So that would leave me with one possible solution, and if you notice, 3 times 3 plus 5 times 0 is in fact 9. 3 times 2 is 6, plus 5 times 6 is 36, minus 1 times 36 plus 36 is 0, and a similar thing holds for the third row. So since there exist C1, C2, C3, not all 0, and there exist, right? Doesn't mean that that's the only one, but you can find, doesn't mean that 0 doesn't work. Because it's a homogeneous system, the 0 vector will always be a solution, but it's not the only one. So not all 0, the set is linearly dependent. A really cool byproduct of the idea of linear dependence is that we can actually not only determine whether the set of vectors is linearly independent or linearly dependent, but we can also tell from our reduction process what subdimension our given vectors span. So what I mean by this is we have a set of vectors in Rn. So that could be in 2 dimensions, in 3 dimensions, whatever. What I'll refer to as the subdimension that we span in that dimension. For example, we know we can span a point sometimes, a line, a plane, etc., is equal to the number of leading ones in the RREF matrix. Furthermore, the space in Rn, so now, well, what do we span in that dimension with these vectors is any linear combination of the column vectors with leading ones. Of course, the exception, when we just span a point is when we have the 0 vector, then all we can span is the origin. So we'll reconsider these 3 examples. And in our first example, if we go back up and we look at the reduced row echelon form of this matrix, then what we found was that there are 2 leading ones. There's a leading one in row 1 and a leading one in row 2. So that means that in R2, since we have 2 leading ones, we have 2 leading ones. We say that the dimension that we span, or the subdimension that we span, is 2-dimensional. Now keep in mind that we are in 2 dimensions, but the fact that we had 2 leading ones means that I span a 2-dimensional subspace. As far as what that implies, if I can span a 2-dimensional subspace of R2, that means that I can make it anywhere that I want. I can make it anywhere in R2. And intuitively, the reason that's evident is that if I just look at these 2 vectors right here, 1, 0 and 0, 1, I already know that I can scale those and put them together tip to tail to get to anywhere that I want. For instance, if I want to make it to the point 5, 6, then I can make it there by taking 5 times the 1, 0 vector plus 6 times the 0, 1 vector, and that will get me to the point 5, 6. The vector 3, 2 doesn't really give me any extra information, meaning that since I can generate the 3, 2 vector by taking 3 times 1, 0 plus 2 times 0, 1, that means the 3, 2 vector doesn't add to my understanding of where I can get. It's an extra vector, but it doesn't allow me to get anywhere that I can't already get to with the 1, 0 and 0, 1 vector. So what is the span of these 3 vectors? The span of the vectors 1, 0, 0, 1, and 3, 2 is equal to, as we're stating up here, any linear combination of the column vectors with leading ones. So what are my column vectors with leading ones? Well, it's the first column and it's the second column. So what are those vectors? Well, it's the 1, 0 vector and the 0, 1 vector. So any linear combination of the 1, 0 vector plus any linear combination of the 0, 1 vector, where C1 and C2 are just any real numbers that we choose. And we know that linear combination gets us anywhere in R2. So the span of those three vectors can be reduced down to just the span of the first two vectors, since those are the columns with leading ones in the reduction. And so any linear combination of those will allow me to get to anywhere in R2. Now, a similar process holds down here. In fact, there's nothing new. This also had two leading ones in our reduction matrix, in our reduced matrix. We got that right here. And it just so happens that in this case, since it's the 1, 0, and 0, 1 vector, the original two columns are the 1, 0, and 0, 1 vectors. So once again, just with these two vectors, that allows me to get to anywhere in 2 dimensions that I want. So anywhere in 2 dimensions, and I can just draw that by shading all of the R2 plane. I can get anywhere that I want. Same reason as up here, but notice that we just don't have the 3, 2 vector. So these are linearly independent. These were linearly dependent, but both sets allowed me to travel anywhere that I want. So the span of 1, 0 and 0, 1 is any linear combination of the 1, 0 vector and the 0, 1 vector. And again, where C1 and C2 can be any real numbers depending on what point I want to make it to. And this allows me to travel anywhere in R2. So again, the subdimension span is 2-dimensional. Or sometimes we write the subspace span, right? Because we're thinking about this is a space that we can travel along, and we can say that the subspace span is 2-dimensional. Now, in our third example, where we had these three vectors, if we look back at our matrix, our reduced row echelon form, we had leading ones in the C1 column and the C2 column. But notice that C3 is not a column that ever has a leading one. In fact, what we noticed was that C3 is a combination of X3 is a combination of X1 and X2. And as a result, since we have once again two leading ones, here's where things get interesting. The subspace span is 2-dimensional. Well, how could we span 2 dimensions in 3 dimensions? We know that a plane is 2-dimensional, okay, even if it cuts through space. So if I use this book as an example, even though this book cuts through 3-dimensional space, you can see it goes this way, it goes this way, it goes towards the screen, it goes away from the screen, but it still is 2-dimensional. I can only move around on this 2-dimensional book. So, since the vectors that have leading ones in their respective columns are the original first two columns, I would say that the span of 9, 36, negative 12, 3, 2, 1, and 0, 6, negative 3, because 0, 6, negative 3 is a multiple of 9, 36, negative 12, and 3, 2, 1, right? Because if I can leave the origin and come back to the origin, well, that must mean that 0, 6, negative 3 is a vector that allows me to come back. So this is going to be any multiple of the first vector plus any multiple of the second vector. And in fact, you could actually say, for what C1 and C2, do these actually generate 0, 6, negative 3? You can actually solve that system and show that 0, 6, negative 3 is actually in the span of these two vectors. So what do we imagine when we're visualizing what this means to span, for the span of these three vectors to just be the two vectors? Well, if I draw x, y, and z, 9, 36, negative 12. We can kind of imagine that to be, 9 units in the x direction. Let's just say that's 9 units. And then 36 units in the y direction. Let's say that that's 36 units. And then negative 12 units, well, that's going to be somewhere down here. So imagine that to be one of my vectors. That's 9, 36, negative 12. I'll denote that x1. Okay, now 3, 2, 1 is another vector. And 3, 2, 1 is 3 units this way, 2 units this way, and then 1 unit up. So it's kind of hard to imagine, but the plane that these two vectors form, let me just try to draw it. Let's just say that this is the plane that I could actually generate. And that has some sort of tilt. It has some sort of tilt in multiple directions. I can get anywhere on that surface that I want. But the problem is I can't actually get off of that surface, right? Because if those two vectors, this one and this one, allow me to travel on that plane, then I would need another vector to be able to get me off of the plane. However, since this one right here is a linear combination of what I'll call x1 and x2, so this is my x2 vector, this little guy that I drew, since it's a linear combination of x1 and x2, this vector right here, 0, 6, negative 3, is somewhere on this plane. 0 units in the x direction, 6 units in the y direction, so it's actually on that plane. And so x3 doesn't allow me to travel anywhere that x1 and x2 don't already allow me to travel to. And that's one of the beautiful outcomes of this theorem, is that since x3 is a linear combination of x1 and x2, proven by the fact that x3 has infinitely many choices for C3, I know that just x1 and x2 allow me to travel everywhere else. And you can see that down here, that any choice of C3, we just have to adjust C1 and C2 accordingly, and C3 will, when added to the multiple C1 of x1 and C2 of x2, allows me to cancel them out and get back to the 0 vector. So just as a little note, in a little kind of recall moment, in R2, the possible spans are a point, a line, or a plane. The plane being all of R2, right? So to span a point, that means I just have the 0 vector, or maybe a bunch of those 0 vectors. Right? I can't actually leave the origin. So this is where we span a point. That's the only way to span a point. If you have a vector that's not the 0 vector, then you can actually leave the origin. And that brings us to case number 2. You can span a line if you have just one vector, or if you just have multiples of that vector. Right? 2, 4 is a multiple of 1, 2, and that just allows me to travel along a straight line. I can get anywhere on that line that I want. The third case is where I have two vectors that are not with the same slope, like for example 1, 0 and 0, 1, but there are other possibilities. This is just the easier case. 1, 0 allows me to travel anywhere right or left. 0, 1 allows me to travel anywhere up or down, and so that means I can get anywhere I want with those two vectors. And so this is where we span the R2 plane. Now, as a last example, we can't really do much beyond R3 because it's hard to visualize. But in R3, we could still span a point, and that's once again just if I gave you the 0 vector, or a bunch of 0 vectors. How do we span a line? Well, to span a line means I have just one vector, or just a bunch of multiples of that same vector, right? These are on the same line. I could also span a plane, but the thing is, that plane is not R2, right? I'm in 3 dimensions. So, for example, if I pick a simple case like 1, 0, 0 and 0, 1, 0, that means that the 1, 0, 0 vector allows me to go in the x direction. 0, 1, 0 allows me to go in the y direction, but I don't have any other vectors to allow me to change my z, so I can actually travel anywhere in a two-dimensional subspace within 3 dimensions, right? These vectors are still 3-dimensional. They because of this 0 component in the z direction, I can't actually change my z at all. So as long as the vectors, the 2 vectors that you have, point in don't point along the same line, and you span a plane. And again, I'm just giving an easy example. I could come up with other ones where this plane is tilted and cuts through 3-dimensional space, as does this one, but still you can't get off of that plane, and so we say that that's a 2-dimensional subspace. Now, there's always going to be another case when you increase the dimension. Well, what's beyond a plane? Well, that's going to be the entire cube, which is the entire R, all of R3. So there are 4 possibilities. There's point, line, plane, cube. And to span a cube just means that I can get anywhere that I want. Okay, here are actually kind of extending the axes. Hopefully you can see that this is really, we can go anywhere we want in those dimensions. Okay, you can actually kind of visualize it like this. You can think about that one octant. I'll call that an octant because there's 8 of them, right? Imagine that this cube represents all of the negative x values, positive y values, and positive z values. Now I have another one down here. I have another one down here, and that would be where I have positive y values, negative x values, and negative z values. Then I actually have another one here, and this is the quadrant that we're most familiar with. It's starting to get kind of messy, but you can kind of picture that cube. That's where I have positive x values, positive y values, and positive z values. Then there's this portion down here. And then there's also all of these other regions here, here, down here, and then back at the bottom. So we call these octants. And I can get to anywhere within that R3, that infinite cube that I want. Now in R4, you can kind of imagine the same idea. And I won't go into detail with this, but maybe just a point, if I have a 4-dimensional vector that has all 0 components or multiples of those, I can just have a line. If I just have one vector, like 1, 2, 3, 4, or any multiples of that, then I can span what's called a, we don't call it we really even shouldn't even call it a line anymore, because you can't draw in 4 dimensions, but we call a plane in higher dimensions, we call that a hyperplane. So let's say I gave you 1, 0, 0, 0, and 0, 1, 0, 0. Well, now I can sort of plot, I can span the x and the y axis, if you will, or the x1 and the x2 axis. And then it gets kind of weird after that, right? Well, what is a hypercube? A hypercube, it's one with a lot of energy. And then I can span all of R4. And then it gets much weirder than that. We don't really talk geometry in bigger dimensions. But I just wanted to give you the analogy in R4.